Okay, should I start?
Please go ahead. And would you rather questions at the end or during the presentation?
Anytime you like. So
Great.
please interrupt me if I'm being confusing. I'm going to turn off my speaker so there's no feedback. But actually, that's not. I shouldn't do that, right? All right. Maybe there's less feedback now.
And can you still hear us?
I can still hear you. Yes.
Perfect.
I'm on
Thank you
different
much.
devices, and somehow there's some feedback, but I'll deal with it. Okay, so I had a brief to present some stuff that I've been thinking about. So next week I'll talk about the actual research, the new stuff. Whereas this week I'll sort of set the context for what I'm doing. I was told to prepare this for third years and up, so I apologize to all the experts in the audience who will be bored during the first part of the talk. But I hope to discuss some new, maybe some new mathematics for some of the experts anyway. So please interrupt me for questions. So in order to discuss what string phenomenology is, I need to talk what string theory is. So this is my standard introduction to string theory. And afterwards, I'll switch to a board talk once my slides run out. So the idea is that our early human forebears, after a successful hunt, looked up at the sky and they pondered the meaning of it all. And they invented physics when they did so. Because the fundamental questions they asked were things like, what is the origin of the universe? Could the universe have been some other way? These kinds of questions are, in modern parlance, asking about the origin and the meaning and the structure of space, time, and matter. So these are the questions that we're very fortunate in our time to be able to answer. And I'll tell you about some of the answers we have to these questions as we proceed. So the questions we want to answer are the questions that sort of inform string phenomenology in some sense. How did the universe begin? Why is the world the way it is? Could it have been some other way? And what's the fundamental explanation for space, time, and matter? So that's what we want to answer. And we want to relate our theoretical models of the world to the actual world that we see. And the challenges here are in addressing issues in particle physics and issues in cosmology. And I'll mention the framework for how we do this. All right, so to start from the very beginning, how do we do physics? We do is we have models, and we interrogate these models and we test them at their limits. So in particular, we're looking for tensions within the theories we have. And a famous example of this is the invention of special relativity. So this is a course I'm teaching right now at WITS. So this is a subject which I'm lecturing on and somewhat familiar with in the moment. The Gedanken experiment is you turn on the headlight of your bicycle, and suppose you're bicycling faster than light, what do you see? This is an experiment that brings Galileo, who tells us velocities add, into tension with Maxwell, who tells us the speed of light is constant in the inertial reference frame. So this tension that exists between the notion of classical mechanics we have due to Galileo and Newton is presented and opposed against the theory of electrodynamics. We want to understand some way to reconcile this tension. So the tension is resolved by a new principle. Principle is that the principle of relativity. The laws of physics are the same in every inertial reference frame. Every observer measures the same speed of light. Maxwell triumphs over Galileo. And ultimately, unlike Johannesburg, the universe has a speed limit, and the speed limit is 2.99 times 10 to the 8 meters per second. So we see that every observer measures the same speed of light, and we're forced into this as a law of nature. So this notion of how theories emerge is one which we see recurrently. Theories always beget theories, and we arrive at special relativity by testing Galilean mechanics against electromagnetism. But we can also do other things. We take Galilean mechanics and add gravity, and the idea that the force which is due to acceleration is the same force that occurs in celestial mechanics led to the law of universal gravitation, and we add gravity to get Newtonian mechanics from Galileo. When gravity is placed in tension with special relativity, we find that we need a new theory. This new theory is general relativity. So by seeing that there are ways to put different theories we have together, we arrive at new models for physics. And these new models are then tested against data. So we do another Gedanken experiment. What happens if the sun suddenly disappeared? The idea of Newton was that action occurred at a distance, and Einstein said that there's a universal speed limit. So if the sun suddenly disappeared, the Earth wouldn't notice for 8.33 minutes, while the consequence was felt when the radiation, light, and gravity reached the Earth from the sun when it suddenly disappeared. And this theory of general relativity has been verified from microns all the way to cosmic scales. The micron measurements are because we do sensitive Cavendish balance type experiments, and the two different masses for which we measure the torque in these Cavendish experiments, these are only separated by about a micron. So that's as far as gravity has been tested at those scales, meaning that in principle, it's possible for there to be extra dimensions which gravitons propagate as long as these dimensions are smaller than a micron in size. And we'll return to this point when we discuss extra dimensions in string theory. So when we put these different theories together, we find that we can put Galilean mechanics in tension with thermodynamics and arrive at quantum mechanics. We can think about how quantum mechanics combines with special relativity, we arrive at quantum field theory. So we have all of these theories that are really a consequence of considering the parameters we turn on and how these parameters interact with each other. So we think about quantum field theory as a modern theory of physics. So the idea behind quantum field theory is that every field has a value at every point in space-time. And examples of this are classical fields. We can think about the Earth, and pressure and temperature have a value at every point in the Earth. So these are classical fields. Similarly, we can think about quantum fields. These quantum fields follow certain algebraic rules, but these algebraic rules enable us to think about particles as local excitations of these fields pervade space-time. So every electron you see in nature is an excitation of the electron field which pervades space-time. So to define a quantum field theory, we need to specify the fields and describe how they interact. There's typically a Lagrangian that enables us to do this, although in higher dimensions, we sometimes encounter quantum field theories without a Lagrangian, and we need to rethink how we structure these theories. But in the simple case, we're thinking about how electrons interact with each other. They interact with each other by exchanging photons. These photons, because the electrons have like charges, have a repulsive effect. You think about time as running vertically in this Feynman diagram. As a result, the electrons exchange photons and they're pushed apart. So we can think about these quantum processes as describing the particle physics that we see in nature. And in fact, the fundamental force is described by a particular quantum field theory. This quantum field theory is called a standard model. It's a gauge theory. It's got a symmetry, SU3 plus SU2 plus U1. It's the best tested theory in the history of science. You make a measurement at 13 decimal places, and you do a calculation at 13 decimal places, and these agree. There's nothing else like it. So even the 1 over r squared in the Newton force law, that exponent 2 has never been measured to 13 decimal places. So the standard model explains all the non-gravitational forces in nature. Explains electromagnetism, explains a weak nuclear force, which is responsible for radioactive decay, explains a strong force, which explains how protons and neutrons are bound together, explains the Higgs effect, which endows particles with mass. So this theory is our theory of particle physics, and we want to understand where this theory arises. So we know that this theory is correct at the experimental scales we can access. We want to understand fundamentally how we arrive at this theory from first principles. We do not have an answer to this question, and next week in my talk, I'll tell you about how to find parts of standard model Lagrangian from a string construction. So in order to get there, I need to tell you about how these string theories are structured and organized, and how we go from the 10 dimensions we predict from string theory down to 4 dimensions. So we think there's one theory of physics. As I mentioned, the standard model covers everything besides gravity. If we think about gravity as a quantum field theory, then we think about what Einstein told us. Matter couples the geometry via this charge called mass. And if we think about two different masses interacting by exchanging gravitons, the same way two different electrons exchanged photons, then masses are pulled towards each other. So the consequence of being attracted when you have the same charge is a property of even spin fields. So it turns out that gravity can't be spin zero. It has to be minimally spin two. And there's a spin two graviton, which sort of makes sense because the metric has two indices when we think about space-time a la Einstein. So similarly, electromagnetism, like charges repel. So the thing which is responsible for this, the gauge field, the photon field, has one index. So it's an odd spin particle that's responsible for this effect. If we treat gravity as a quantum field, we think about a graviton as being responsible for pulling masses together, we can do similar calculations a la Feynman and figure out these amplitudes for these interactions. What we find is that when we do this, any amplitude we construct and we calculate, if we go to enough loops, this turns out to be infinity. At zero loops and one loop, it's finite, but at further loops, the answer is always divergent. And this is not the kind of divergence we can fix using normalization because the coupling constant associated to the gravitational force is negative mass dimension, unlike the coupling constants we associate to the renormalizable forces. So as a result, the renormalizability of theory is something which does not fix or render these infinities benign. We're stuck with this calculation, which we can't really make sense of because it says there's any two masses. When we think about how they interact gravitationally in the full theory, they give us results that are nonsensical. We can imagine as a solution to this sitting at some ultraviolet fixed point for gravity. Weinberg mentioned this is a possibility, and people have examined whether this possibility is viable. So far, I don't believe it's been definitively ruled out, but no one really thinks this is likely, that there's a strongly coupled fixed point that we just happen to be sitting at where you can make sense of gravity in some field theoretic sense. We're sort of stuck, I think, with the idea that theory is non-renormalizable. So what went wrong in treating gravity as a quantum field theory? General relativity is the dynamical response of geometry to the presence of matter or energy, and conversely, the dynamical response of matter to the curvature of space-time. In a quantum universe, things fluctuate at small scales. We know this due to the uncertainty principle, and because space-time itself fluctuates at the quantum level, one of the central assumptions of general relativity, the geometry is smooth, and the differential geometry structures that would enable us to write down the Einstein equation, for example, these break down at very small scales. So ultimately, because the assumptions are problematic at some level, the idea that quantum field theory is the organizing principle for gravity just fails. So we need to come up with something better. We've seen the solution in quantum field theory itself. If you think about the Fermi theory of beta decay, we had a 4-point fermion interaction. That vertex also turns out to be non-renormalizable, and the way that you fix that problem is you smear out the interaction. You think about two particles interacting via a boson, either an intermediate vector boson or a photon or whatever, and we think about the interactions being smeared out, and that renders things finite. We use the same idea to resolve this infinity that we encounter in quantum field theory. So the way I've structured things, a la these different theories we've studied, they really relate to turning on different parameters. So Bronstein had this observation that the way physics is structured, there are three parameters. There's h bar, which gives us the quantum world. There's 1 over c, which gives us special relativity. And there's g Newton, which gives us gravity. So you can turn on one of these, you can turn on several of these at the same time. And when you do this, you find the different theories we have. So general relativity, for example, is the consequence of turning on a finite speed of light along with a Newton constant. And quantum field theory is the consequence of turning on h bar along with a finite speed of light. If we turn on everything at once, you get this quantum gravity, which we don't know. And we would like to understand the structure of quantum gravity a bit better and figure out how to realize our real world in this framework of quantum gravity. So we've noticed the gravities of quantum field theory gives us infinity, and we follow the same notion of smearing that we saw in four Fermi theory, and we render our interactions finite by smearing them out. Instead of thinking about particle excitations, we think about string excitations, and we think about the mediating particles as not being particle-like either, but also being stringy in nature. The consequence of this is that the amplitudes you calculate in string theory at all loops turn out to be finite. There's a price you pay. Whereas we're working in quantum field theory and quantum gravity in a naive way, we're working in 4 dimensions. Whereas when we think about the consistency of string theory, this consistency demands we work in a higher number of space-time dimensions. And superstring theory, in fact, lives in 10 space-time dimensions. And in order to prove this fact, we rely upon some interesting mathematics. There's a certain limit in which the sum of the integers is not infinite, but it's minus 1/12. And you can think about this as a zeta function regularization of the sum. And it turns out this is crucial to defining some particular Casimir or central charge for a conformal field theory, which lives on the string world sheet. And this particular central charge is responsible for the calculation that the string theory is only consistent in 10 space-time dimensions. So
when you say string theory lives in 10 or 12 dimensions, what exactly do you mean by that? Do you mean there's like a natural dimension that just pops out somehow, or yeah, I'm not sure what's that.
yes, that's exactly what I mean. I mean that when you think about the string theory is described by a theory of quantum fields that live on the string world sheet. So let me draw a picture. We have these strings that are propagating in space-time. So there's a direction of the string, which I'll call sigma, and there's a direction of time, which I'll call tau. So this is a 1 + 1 dimensional string world sheet. On the string world sheet, there are quantum fields. So for example, there are these fields x mu. This x mu, so I'll call the string world sheet sigma. This x mu supplies a map from sigma to space-time. And mu runs from 0 to d. So I'm working with a space-time which is d + 1 dimensional. So you can think about these coordinates of the string in space-time as being described by these fields x mu, which live on the string world sheet. Now I've got this quantum field theory on the string world sheet. And I want to make sure this quantum field theory is consistent quantum field theory. And the consistency of this quantum field theory fixes d, the number of dimensions in space, and therefore the number of dimensions in space-time. So it turns out that in a bosonic theory, d is 25, so space-time is 26-dimensional. If you include fermions on the world sheet as well, the consistency is that d equals 9, and therefore the space-time dimension is 10. So the fact that string theory has to be consistent as a quantum field theory tells us then about the dimension of the embedding space in which the string is moving. Now, the consistency of string theory, the fact that this quantum field theory is conformal, gives us an equation for the beta function for that quantum field theory. And this equation for the beta function for a particular field associated with the graviton, the embedding of this string in space-time, this tells us that the metric in space-time is the one which solves the Einstein equations. So when people say that string theory is a theory which gives you gravity in space-time, this is what they mean. They mean the quantum field theory on the string world sheet is a conformal field theory, because this conformal field theory, the beta function vanishes. The equations governing the vanishing of the beta function are the same as the equations of Einstein in the ambient space-time M. Does that answer your question?
Yeah.
Good. So let me go back to where I was.
Sorry,
So,
I have a question. What do you mean
smearing? What does that term mean?
So what I mean is that if I had the four Fermi interaction, I would have psi, 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 psi. My Lagrangian would have a term which was, there's a coupling constant here, G, psi 1, psi 2, psi 3, psi 4, maybe some bars here, but there's some term which looks like this. The Lagrangian contains such an interaction. The Lagrangian also contains an interaction which looks at psi bar d slash psi. So this is a kinetic term for this field, psi. From this, we conclude that psi has a mass dimension of 3/2. So since there are four psis here, the mass dimension of these four psis is 3/2 times 4, which is 6. This is Lagrangian. The action associated with Lagrangian is d4x times L. And this term has dimensions of action where in units of h bar equals 1, this is dimensionless. So x to the fourth has mass dimension -4. So all the terms which appear in this action have to have the same mass dimension. And because the kinetic term that appears in the action, we conclude that in order for this to work, the mass dimension of G has to be -2. If the mass dimension is negative, it turns out these interactions lead to quantum field theories that are not renormalizable. You always get these infinities. So you smear out this interaction by saying that you have something like psi bar psi, and you smear this out with a photon, and you have psi bar or whatever in your Feynman diagram. So you smear out this point-like interaction by making this spread out via this intermediate particle, which could be some W or some photon or whatever. So the analog of this is that when you had these masses interacting by exchanging gravitons, you think about promoting this to the interaction of strings, and you have some string exchange, which is responsible for this interaction. So that's what I mean by smearing things out. Okay.
Yeah.
Okay, good. So in smearing out the interaction, then, we get things that are finite, and we're working in a particular dimension of space-time that we conclude from requiring that the quantum field theory we're studying is conformal field theory. So it turns out there are multiple ways of doing this. So in superstring theory, in 10 dimensions, there turn out to be a number of different consistent theories, and they go by various names. We're not very creative at naming things, so some of these are called type 1 and type 2a and type 2b. So those are particular string theories. And there's also something called heterotic string theory, and there's a gauge group associated with heterotic string theory. And you can only have particular gauge groups in order to cancel certain anomalies in the theory. These gauge groups turn out to be E8 cross E8 or SO32, which means spin 32 mod Z2. Now, it seems a bit unsatisfying to have 5 or 6 different quantum field string theories in 10 dimensions. So you want to come up with some structure which is an umbrella for all of these. And this is proposed to be an 11-dimensional theory that lives in one higher space-time dimension. You think about the coupling associated to string interactions as being given to us by an extra dimension, and this leads us to M theory. And the different limits of M theory that are perturbative are all of these different string theories. And there are these dualities which relate the string theories to each other and to M theory. In addition, you can think about certain complex structures to describe symmetries of these string theories, and you can promote these complex structures to physical dimensions. And if you do this, you can think about lifting a 10-dimensional theory to a 12-dimensional theory. So there is also a 12-dimensional story about F theory, which is also useful in string phenomenology, and I'll say a few words about that at the end. So the question is, ultimately, though, that if string theory is a higher dimensional theory, and we only see 4 dimensions, how does this happen? How do we get this low-dimensional physics in 4 dimensions from string theory? And this is a subject of string phenomenology, making contact between observations of string theory, or the predictions of string theory, and the structure of string theory to observations about the real world in 4 dimensions. And by real world, I mean 2 aspects of the real world. I mean particle physics, and I mean cosmology. Okay?
Sounds great.
So we see, as we said, there are forces of nature. These forces of nature, the gravitational interactions a la Einstein. We understand how to get these gravitational interactions a la Einstein from a fundamental theory. So we're after some aspects of the fundamental theory that we haven't fully recovered. That's really the evolution of the universe cosmologically. That's a solution to this Einstein equation in space-time. And secondly, the Standard Model as the organizing structure for particle physics that we observe in experiment. So there's a theorem that runs into a difficulty for us, and fortunately, string theory provides the resolution to this difficulty you run into. A theorem is due to Cohen and Mandula. A theorem basically says the symmetry group in 4 dimensions for quantum field theories is the Poincare group, which is sort of the structural group behind quantum field theory ab initio, and any internal symmetries that may exist. In particular, the theorem tells us that non-gravitational interactions are not encoded as geometry in 4 dimensions. So you need to go beyond the standard notion of geometry in 4 dimensions in order to get these non-gravitational interactions, for example, the ones we see, the gauge interactions in the Standard Model. So the paradigm for evading this theorem is given to us very early. In the 1920s, for example, people were already thinking about unified theories, and the clever loophole is the internal symmetries that the Cohen-Mandula theorem allows. These can be obtained from higher dimensional geometry. And the simplest example of this is using the 5D Einstein equations, an empty flat space. You think about the flat space as being a Minkowski space, R1, 3, times a circle. And the Einstein equations in this 5-dimensional space, if the circle is really, really small, it lets us have an effective field theory or an effective theory of nature in 4 dimensions. In this effective theory in 4 dimensions, we get the Einstein equations plus the interactions associated with electromagnetism. And the reason is electromagnetism as a gauge theory is a U1 theory. So the symmetry, Lie group associated to electromagnetic fields is U1, and U1 turns out to be a symmetry group of the circle. U1 is simply the group of phases on the complex unit circle in the plane. So this symmetry group is rotationally invariant. Its rotational invariance is this S1. So by thinking about a 5-dimensional theory that includes this compact circle, we get a theory of 4-dimensional physics that is Einstein plus electromagnetism. So Einstein-Maxwell theory comes from Kaluza-Klein compactification. So we can think about maybe using the same idea. We start with a 10-dimensional theory. We have some compact space. This compact space is the 6-dimensional now, and then we get an effective theory in 4 dimensions, and we want this effective field theory to be the theory that describes the physics that we see. So string phenomenology, then, is a subject which describes how to go from 10 to 4 dimensions in this particular context. Okay? Good. So the thing we look at is somehow geometrically engineering the 4-dimensional theory we want from this higher dimensional theory. So we know that 10-dimensional theory is consistent. We make some ansatz for the theory in 4 dimensions. We see that things approximately look like Minkowski space. So we think about Minkowski space times some compact manifold. This compact manifold will turn out, it's called a Calabi-Yau manifold. I'll tell you about Calabi-Yau manifolds shortly, and I'll tell you about finding metrics on Calabi-Yaus in the next talk. But for our purposes, our ansatz for the geometry is there's this flat space times some compact space. And because we want a particular theory of particle physics, just like we use the compact space being a circle to electromagnetism, in order to get the particle physics we want, we need to choose this compact space appropriately. And it turns out with certain properties of this compact space, translate directly to the physics we see at low energies. For example, a number of generations of particles of light fields that we see is related to the Euler character, a certain topological property of this compact space.
Sorry, just to check.
Yes.
So when we took the product of the Minkowski space and the circle, and we got electromagnetism sort of coming out, since the gauge group of electromagnetism and the circle will have the same symmetry, or are the same symmetry group. So if we then want to include something like QCD, do we need to embed like a QCD gauge group in that way, or is there now like a separate technique that we could use?
So yes, there is indeed a separate thing we do, and I'll explain this more next time. But the idea is that the string theory we're going to study is this heterotic theory. It's heterotic EA cross EA theory. And my pen seems to have died. This will be a problem. So I've got this EA cross EA theory, and this Calabi-Yau manifold, it turns out, is an SU3 holonomy manifold. So I don't want to explain very carefully what holonomy means. We can think about this as a symmetry associated to this Calabi-Yau. This SU3 holonomy means that there is a complement, if you like, to SU3 and E8. That complement turns out to be E6. And this E6 we interpret as a grand unified group, and SU3 cross SU2 cross U1, standard model gauge group, embeds in this E6. So that's how you get the gauge group associated to the standard model from the string construction. I'll say more about this next time.
Yeah. Maybe, sorry, just a quick follow-up, because I think that's a really interesting question. So could one look at Minkowski cross something simple, similar to a circle, and get, say, just the weak theory plus gravity, or something that is just QCD plus gravity, or maybe Yang-Mills plus gravity?
I think you can probably do this. I don't know of anyone who's actually done it, but this is certainly a plausible idea.
Okay, thank you.
So life becomes more complicated, and this is going to be implicated when we discuss cosmology. And the reason is we don't live in R1, 3. Our universe today most closely resembles de Sitter space. De Sitter space is a problem for many reasons. So I told you that our 10-dimensional theory is got fermions in it. And in fact, these fermions are related to the bosons. They're not independent of each other. They're related by a symmetry called supersymmetry. And de Sitter space is incompatible with supersymmetry. So we need to go through some new contortions. We need to find some new physics that enables us to find a de Sitter solution to a superstring theory. So de Sitter space is non-supersymmetric. There's certainly non-supersymmetric solutions to a supersymmetric theory, and we just need to find the appropriate one, and this presents its own challenges. And I'll talk about that a little bit later on in this talk. All right, so to summarize so far, string theory supplies a framework for quantum gravity, and within this framework, we're beginning to understand things like black holes and the holographic correspondence, and how space-time degrees of freedom are encoded. And we're also finding a string theory is a very powerful tool for doing mathematics. So this is one of the circumstantial pieces of evidence that string theory is on the right track, because it's inventing all sorts of beautiful mathematics. And it can't be the case that this useless theory is somehow telling us something very, very deep about mathematical structures independent of physics. The problem of finding our universe among all the possible ways to go down from 10 to 4 dimensions has a name. It's called the vacuum selection problem. And it's a problem which is rather outstanding. We don't really have a solution to this yet. We can get aspects of particle physics from string theory by choosing the appropriate Calabi-Yau compactification. We can get aspects of cosmology from string theory by choosing the right frameworks, but we don't get everything at once. There's no theory that we found in 4 dimensions from string theory that's consistent with every observational fact that we have about nature. In fact, we don't have even an inkling of how to combine cosmology with particle physics in any sensible way that works, even in a very artificial sort of manner. So the problem is exacerbated by the fact that most vacua that we obtain in 4 dimensions from a string compactification, they resemble nature not at all. So we need to find some framework which enables us to get closer and closer to the real world. So we'll start with the unreal world. So what I want from the unreal world is a supersymmetric theory, a theory which has bosons and fermions that are mass degenerate. This theory, again, is incompatible with de Sitter space, so we need to go through some contortions later on to get a de Sitter solution from string theory. We want the correct gauge group for the standard model. We want the right kinds of matter that appear in the standard model. We want the right kinds of interactions that appear in the standard model of Lagrangian. And we want 3 copies of matter such that the couplings associated, the masses of the particles, for example, are not identical. And we want this to be consistent with cosmology, at least in the sense that it accommodates inflation in the early universe, even if we don't know very much about the cosmological constant in the de Sitter phase today. So that's what we're initially after. As I mentioned, supersymmetry is a symmetry which relates fermions and bosons. And this is also maybe a problem because there's no experimental evidence for supersymmetry at the Large Hadron Collider. The hope was that at the energy ranges probed at Large Hadron Collider, say around 10 TeV, we would, or 1 TeV, we would see that there would be the Higgs and there would be some candidates for superpartners that are partners to the particles we know in nature. We know the supersymmetries must be a broken symmetry in nature because we don't see a particle which is a fermion with the same mass as the a boson with the same mass as the electron, or a fermion with the same mass as the W. Such things don't exist in nature that we've seen. So as a result, this symmetry must be broken somehow. And we don't know a mechanism for, we know several mechanisms. We don't know which mechanism is chosen, assuming supersymmetry even exists. Supersymmetry really only has theoretical arguments going for it. One theoretical argument that supports the existence of supersymmetry is that the Higgs mass is very, very small compared to the fundamental scale. The fundamental scale is set by the constants of nature, the Planck mass, this Planck mass is orders of magnitude, many, many orders of magnitude, larger than the scale associated with electroweak symmetry breaking, which is accommodated by the Higgs. So we want to come up with some way to explain the separation of scales. And supersymmetry gives us a way to explain the separation of scales and explains why the Higgs mass doesn't get huge radiative corrections that make its mass supermassive. So it's a good idea. And we see that it's a natural idea that arises in string theory, but we don't see experimental evidence for this in the laboratory. So this is another sense in which this world we're looking after or looking for is unreal. There's no way to accommodate the kinds of supersymmetry we would have liked to have seen with the experiments we have seen. It's a pity, but that's where we are. So the reason why these clavials are useful is that they admit what's called a Ricci flat metric. So we want a solution to Einstein's equations. One solution to empty vacuum Einstein equations is the curvature vanishes. R mu nu equals 0 is a solution to the vacuum space Einstein equations in any dimension. Now, we know the Minkowski space then has R mu nu equal to 0. So just like R3, 1 is a solution to the vacuum Einstein equations in 4 dimensions, R9, 1 is a solution to the vacuum Einstein equations in 10 dimensions. We want to see 4-dimensional physics arising from 10-dimensional physics, so we don't want R9, 1. We don't want flat Minkowski space in 10 dimensions as a solution that we select. We want to pick some other solution that also has the property that R mu nu equals 0. We can multiply, we can think about Minkowski space in 4 dimensions, R3, 1, times a manifold, which also satisfies R mu nu equals 0. These Calabi-Yau spaces have this property. Their Ricci tensor vanishes. The Riemann tensor may not vanish, but their Ricci tensor vanishes. The Ricci tensor is a tensor which appears in the Einstein equations, so that's the one we want to vanish anyway for a flat solution. The upshot of having such a Calabi-Yau solution is that because the solution is flat, it ensures that in 4 dimensions, we retain what's called n equals 1 supersymmetry. For each particle we see in 4 dimensions, there is a superpartner. So this is the kind of framework in which we would like to have seen what's called the minimal supersymmetric standard model, the minimal supersymmetric extension of the particle physics that we see in the experiments. Now, it turns out that topological and geometric features of this Calabi-Yau relate to aspects of the Lagrangian in 4 dimensions. In particular, the particle spectrum and the kinds of particle interactions we see in nature, these are related to the topology of this compact space. And the actual couplings which appear in the Lagrangian, which tell us how strongly the fields interact, these are related to the geometry of this Calabi-Yau space. And it's the latter point which I'll discuss next week. Okay, so what's a Calabi-Yau? A Calabi-Yau is a geometry with a nowhere vanishing holomorphic n-form. And a Calabi-Yau n-fold is such a space. By n here, I really mean 2n real dimensions. So this n represents the number of complex dimensions. So it's a complex manifold. For differential geometers, they may prefer a definition that the canonical bundle on this space is trivial. That's another way of describing the Calabi-Yau. And you can also say there's a Kähler metric holonomy in SUN. I was talking about SU3 holonomy. I was talking about Calabi-Yau threefold or a 6 real dimensional space in order to go down from 10 to 4. So for the remainder of the talk, the last 15 minutes or so, I want to tell you something about Calabi-Yaus so that next time we can discuss how we do some compactification and find some metrics on these spaces and work down to 4 dimensions. Okay, so the simplest Calabi-Yau is a Calabi-Yau one-fold. This is the torus. So this geometry is a geometry with topology. So there's a genus, there's a hole in the torus, and you can think about wrapping a rubber band around that hole in the middle, and that rubber band is not contractible once you wrap it around because the torus has a certain size associated to that cycle. So you can map this torus into a flat geometry. So this torus is an example of a space which solves the Einstein equations in flat space. It's got a vanishing Ricci tensor. And the reason is you can think about the torus as an old school video game where you have periodic boundary conditions, both left to right and top to bottom. You disappear at the top, you reappear at the bottom. That's essentially the structure of these cycles which appear on the torus. There are 2 parameters you use to define a torus. One is the area. So it's the area of the fundamental domain in the complex plane to which your torus is mapped. And the second is the shape of your torus. So when you think about periodic boundary conditions, you needn't think about periodic boundary conditions being on a rectangular screen. You can tilt your screen to be a parallelogram and still have periodic boundary conditions in the parallelogram. The amount of tilt is the shape of the torus. So these 2 parameters, the area and the tilt, the shape, describe the torus completely. And these parameters have names. And we call one parameter the Kähler parameter, the area. It describes the size of the torus. And the other, the complex structure parameter, tau, describes the tilt of the torus, the shape. So these, the simple Calabi-Yau in the Calabi-Yau one-fold in 2 real dimensions has 2 parameters, area and complex structure parameter tau. Now, we want to work with geometries in 6 real dimensions, so 3 complex dimensions, and these are characterized by more parameters of this type dimensioned. So in particular, you can have arbitrary integers. Well, they're not quite arbitrary, but you can have 2 different integers you associate to the complex structure parameters and the Kähler parameters. Now, the Kähler parameters, again, are the size parameters. The complex structure parameters are the shape parameters. And these are given names. They're called Betti numbers or Hodge numbers. They're associated dimensions of certain homology groups you associate to these geometries under consideration. And these are organized in what's called a Hodge diamond. But the important feature that we want to consider is that there are 2 parameters we describe any 3 complex dimensional Calabi-Yau. So these are H11 and H21 or H12. There's a symmetry associated to what's called, well, complex conjugation, which lets us reverse H12 with H21. Similarly, there's a symmetry associated to Poincare duality lets us flip H11 and H22. The H12 measure parameters that are related to the shape of our geometry, and the H11, these measure parameters related to the size of our geometry. So just like there was one parameter of each type for a torus, now there are more such parameters for a Calabi-Yau threefold. Now, the Euler character, so the Euler character of the torus, so chi is equal to 2 minus 2g, where g is the genus. So the Euler character of the torus, genus 1, there's one hole in it. The Euler character of the torus was 0. The Euler character of these Calabi-Yau threefolds is given to us by considering these Hodge numbers H11 and H12. In fact, the difference of these Hodge numbers times 2 is the Euler character. You'll notice that we have this diamond of integers, and this diamond can be flipped 90 degrees. We flip the diamond 90 degrees, we're exchanging H11 with H12. This gives us a new Calabi-Yau with the number of complex structures and the number of Kähler structures, Kähler moduli we call them, they're flipped with respect to the original Calabi-Yau. This symmetry is called mirror symmetry. And it turns out that string theory gives us the same effective field theories upon compactification on a Calabi-Yau and its mirror when we think about the context of what's called type 2 string theory. So type 2a string theory, compactified on a Calabi-Yau, is the same as type 2b string theory, compactified on the Calabi-Yau's mirror. This is a symmetry in the theory that's related to T-duality, which lets us relate compactifying the theory on a circle to compactifying a theory on a circle whose radius is 1 over the radius of the initial circle. So symmetries of string theory are manifested in how we get low-energy theories upon Calabi-Yau compactification. Okay, so I've run out of slides. Let me just talk a little bit then about Calabi-Yaus, and next week we'll discuss how to go to low-energy physics. So these Calabi-Yau spaces, we don't know how many there are. And we know that there are 30,108 unique choices of H11 and H21. These moduli I discussed previously, the Kähler moduli and the complex structure moduli. There are 30,108 choices of these. And there are ways of getting Calabi-Yaus from what are called reflexive polytopes in 4D. And the number of reflexive polytopes is about 500 million. So the way to get a Calabi-Yau from a reflexive polytope, I don't want to define what these things are carefully. You can ask me if you like. But to go from a polytope to a Calabi-Yau requires us to triangulate the polytope. And the triangulation, for example, means choosing how to triangulate a square, for example, in a consistent way with all the other faces of your polytope. And these different consistent triangulations all give us a different Calabi-Yau. So as you can imagine, if you take a polytope with in 4 dimensions, with lots and lots of faces and lots of edges and lots of vertices and so on, there are lots of different ways to triangulate these things consistently. And each of these ways of consistent triangulation gives us a Calabi-Yau, and we don't know how many Calabi-Yau triangulations there are, so we don't know how many Calabi-Yaus there are in total. And there are ways to get Calabi-Yaus from things which aren't reflexive polytopes as well, so we don't know how many Calabi-Yaus there are. We expect there are lots and lots of these. And in addition, we can put in, so we noticed on the torus that there were these cycles. We can imagine wrapping strings or higher dimensional objects in string theory called branes around these cycles. And you can interpret these wrapped branes as flux through a cycle. And this is just an analog electromagnetic flux we see in E&M. But if you include these fluxes, there's some number people have approximated, maybe. This is sort of a made-up number. There's no theoretical derivation of this. But this number indicates there could be 10 to the 500 Calabi-Yau compactifications from 10 dimensions down to 4 dimensions. 10 to the 500 is an astronomical number. In the visible universe, there are about 10 to the 80 protons. So this is orders of magnitude more than that. One solution to the vacuums problem, the vacuum selection problem, is that the difference between the Planck scale and the scale that we see the cosmological constant in nature. So we take lambda to m Planck, that ratio to the fourth power, this is about 10 to the minus 123. So if you have 10 to the 500 possible solutions, you have 10 to the minus 123 as the difference between the cosmological constant we see in nature and the Planck energy, then it's not so bad. There are 10 to the 300 some solutions that fit the data. This method of solution is anthropic selection. We live where we can live. We live in a universe with this particular cosmological constant among all these possibilities. And, it's not, it's rare, but it's not especially untoward to expect that we happen to live in one of 10 to the 377 possibilities or whatever it was. So this is a solution we can imagine to the vacuum selection problem. It's unsatisfying, but it's a solution. We would like to do better. So as I mentioned, there are two chief issues. The first is particle physics. And the best way to get particle physics is Calabi-Yau compactification. Just like we had Kaluza-Klein compactification previously. And this Calabi-Yau compactification transpires on one of these geometries I mentioned, and we get a gauge theory out of this. And the context of string theory where we do this is this E8 cross E8 heterotic string. So these are the nearest theories to the real world we have on the particle physics side. If we want de Sitter space, arguably the best constructions we have in de Sitter space are in type 2 string theory. And these constructions of de Sitter space in string theory, these are somewhat controversial since people don't know whether de Sitter space is actually a stable solution to string theory. But there are reasons to believe that this is certainly worth exploring. So we don't know the answer. People have different views on this. It's somewhat political in the community as to whether de Sitter space is a possible solution. But the idea then is we take this type 2 string theory and we compactify on Calabi-Yau in this type 2 context, and then we find a de Sitter-like solution to string theory upon compactification. And you may have to go to ADS, anti-de Sitter space, and then lift de Sitter space as a possible avenue to get this kind of cosmological solution. Now, there are string dualities which relate the heterotic string to the type 2 string. And we can imagine that the construction we have in one context is realized in the other context as well. But as I said, we do not have any construction which gives us a chiral theory of particle physics which is somewhat reasonable and a reasonable cosmology at the same time. So it's an outstanding challenge to put these two pieces together. That's the current status of string phenomenology, I would say. We have ideas for how to do each of these things, but no ideas for how to do everything at once. So next time, I will talk about how to get standard model-like gauge theories from this heterotic string. I won't have very much to say about cosmology, but that is something I'm thinking about. So I've been talking for an hour now, roughly, so let me stop there. Thank you.
Very good. We had some questions during. Jared did the nice introduction. You can be the master of ceremonies in the Q&A, but it might be a little bit difficult with the people. But I guess we can see through the video. Do you want to try to run things, Jared?
I think I can't really see everybody's off the screen or anything, so I think I'll leave it up to you all.
Okay, fair enough. Are there further questions for Vishnu? Yeah, please go ahead.
This is maybe just a case of pushing metaphor too far, but when you talk about smearing interactions as a sort of motivation for considering strings as opposed to particles, I'm not sure I fully understand why particles and these interactions are smeared into strings instead of some sort of extra intermediate. you know, why don't we just have like another loop in there, for example?
Or like a W or Z for the lead force.
Something, yeah.
So if we have this interaction, G Newton, roughly, so let me try this again. Let me think about the field theory where this comes from. The field theory where this comes from is the Einstein Hilbert action created as a quantum field theory. So this is d4x root minus g r minus 2 lambda, say. So that's the Einstein Hilbert action that we're considering. Now, r is a curvature. It has two derivatives with respect to position in it. So r is dimension m squared. This d4x is dimension m to the minus 4. So in order for this to be an action, this means that 1 over 8 pi g Newton has to be dimension m squared as well. So g Newton is dimension m to the minus 2. I'm working in units where h bar equals c equals 1. So in these units, the coupling constant you associate to this interaction is negative mass dimension. Such interactions are always non-renormalizable. So you can't fix this theory by smearing it in a particle-like way. It just won't work.
But wouldn't that have been the same argument for the Fermi theory?
Yeah, but the Fermi theory, you replace this interaction with something else. If you can come up with a way to consistently replace the Einstein-Hilbert action with something else to use the same gravitational theory, then maybe this would be a way ahead. But there's no such thing we know of.
I mean, right, what you do with the full Fermi interaction, the dimension of the G comes from the propagator of your exchange particle, right? That you do I don't know, short distance propagation limit on to get the full Fermi interaction, right? So you would have to separate things there and stick something in between. But how do you separate that action? That's essentially the issue.
Yeah.
I mean, you still can use this as a low energy effective theory if you want to, and then generate right high induced vertices, right? In the usual way, if you have something non-renormalizable, you get a tower of interaction and you get a tower of things that you need to fix, but it's only this far where you probably gain anything by doing that.
Okay. Yeah.
Other question? And definitely for the young folks, please ask questions. Part of your academic growth is at some point in your career you'll be at conferences and you want to ask the big shots questions. So this is the parlance of the youth's safe space to start getting practice doing that. But I think
very much thought, but please do ask questions.
yeah. And go ahead, Jared.
I just would like to know, the heterotic string, which sector does it live in of your, is it, because you have the RR sectors and the...
Right. I'm really looking at, so the RR sectors and the NSNS sectors, you typically think about these as properties of the type 2 strings. The story's a bit more complicated than heterotic string. You think about a bosonic direction, you think about sort of a tensor that with a set of directions you associate to supersymmetry oscillators. So it's a bit more complicated structurally. I can explain this in more detail later if you like, but we just leave it at that for now.
Yeah.
Yeah, please go ahead.
Perhaps a silly question. But so this problem 2 that you're talking about here, the fact that we have de Sitter space as opposed to R13, that's I want to say that's a problem for cosmology people. We don't really have to we don't really have to touch that in particle physics.
That's right.
To my
But we
understanding.
like string theory to explain everything, rather than just something or some bits of things. We'd like to explain both the cosmology we see and the particle physics we see in a single framework. So that's why this problem arises in string theory.
Right.
We also like to, we know that these Calabi-Yau spaces, they've got these moduli associate to these theories, these complex structural moduli, these Kähler moduli. I can interpret these moduli as being fields in the low energy theory, scalar fields in low energy theory. So you can imagine some of these moduli being inflatons in the early universe. And you can also imagine these fields being things like inflatons now, quintessence fields, if you like. And these may explain aspects of why things look de Sitter-like without actually constructing a de Sitter geometry.
Right. Well, my thinking is how the attempts to build something like a local string theory to try and say, rather, let's look at flat space and see what we can work out from there.
Yes, I mean, certainly that's what we do when we think about particle constructions in this Durham model. I'm really thinking about the context of constructions in R1, 3 crosses Calabi-Yau threefold. And part of the reason I'm doing this is I want n equals 1 supersymmetry in 4D.
Yeah. Okay. Maybe just to follow up on that, maybe I missed it, but what is the experimental justification for this strong statement that you made that the universe's symmetry group is not R13, but rather de Sitter?
That's observation. We're seeing that the universe is accelerating expansion. That's consistent with a positive cosmological constant in de Sitter space. In de Sitter space, the conformal diagram in de Sitter space doesn't have a global time-like Hilling vector. And the absence of this global time-like Hilling vector means you can't have supersymmetry.
Okay, can I not have, because the universe is also flat, measured flat, can I not have an expanding universe that's flat that's R13?
The universe has a positive cosmological constant, or appears to have a positive cosmological constant. That means it's de Sitter space, it's not flat space. We're not living in R1, 3 cosmologically. We're living in something which looks like de Sitter 4.
What? So I definitely, right, obviously the universe expands, like there's no bubble on that, sure. But I thought that there was the various omegas, the content, the dark matter, dark energy, so on and so forth.
Right. So omega m plus omega dark energy is approximately 1. This means the spatial sections are flat. This does not mean the geometry of the universe is flat.
Okay. Yeah. Great. Other questions?
Yeah.
I have a question about these Calabi-Yau manifolds. I think you settled on them pretty quickly, as it was like you start with R1, 3 and then cross the Calabi-Yau, and that can kind of recover the symmetry of the standard model. And then there's a lot of different ways you can compactify that, and that gives you the 10 to 500 number. I'm kind of curious, like, are there a lot of different choices you could have made there potentially, or are you really forced with Calabi-Yau? Like, should this 10 to 500 number be even larger, or
certainly? I mean, if you want to, so the reason you use a Calabi-Yau is to get an n equals 1 theory in 4 dimensions. If you say that I never had n equals 1 supersymmetry to begin with, we should go for an n equals 0 theory, then the Calabi-Yau manifold needn't be the only choice for compactification. You choose other manifolds for compactification, and as a result, you can get lots of more possibilities.
Okay.
So,
Okay, thanks.
I just have two quick questions. So if I understand correctly, Calabi-Yau are Kähler manifolds, right?
yes.
So is there and Kähler geometries kind of naturally arise from looking at, say, a non nonlinear supersymmetric model. Is there a relation there? Like,
right. So Kähler manifolds, let me see how I can answer this. So we're working at complex manifolds, first of all.
Mm.
When you work with complex manifolds, you can define your Laplacian in a bunch of different ways. And it turns out that these different ways of defining the Laplacian all turn out to be the same when you're talking about Kähler manifolds. So this is the reason we're looking at Kähler complex manifolds. Another reason why we're looking at Kähler complex manifolds. Kähler geometry makes things simple in some sense. So that's a way, it's a reason for looking at these kind of particular geometries as opposed to others.
Thank you. And I've just seen like some old material, but as people used to think of orbifolds as the possibility to get these the compact sides that's kind of fallen out because of the Cabral.
I will discuss orbifolds that are freely acting next time as well. So an orbifold, for people who don't know, is you take some point x on your space and you identify with some other point x prime on your space. And typically x prime is given by the identification of some group action on your initial point x. If under the group action you identify all points that are related by such an action as equivalent, you get an orbifold space. So the simplest example is to just take the real line, x, and then you identify x with minus x. And this gives you the half line. That's an orbifold of the real line. Because you're thinking about the point 3 and the point minus 3 as being the same point. Now, such an action where you identify x with minus x has a fixed point. 0 gets mapped to itself. So that fixed point turns out to typically be singular in these orbifold actions, upper actions. If you think about a freely acting group action, such that there's no fixed point, you still make such an identification, then you get smooth geometries. And those will be the smooth geometries, smooth orbifolds I'll be looking at next time.
Last question. We just throw out one more. So why is it 4 dimensions? Is I think an interesting question. So why is it 3 large spatial dimensions? And I wonder, you mentioned Coleman Medulla, sorry. Do you think that might have some hint into why it's 4 large space and time dimensions?
So this is an open question. We know that things are special in quantum field theories in 4 dimensions. So this, because 4-dimensional quantum field theories are somehow special, there's maybe a natural reason why the quantum field theories we encounter are 4-dimensional. In addition, there's something called a Brandenburger-Waffe mechanism. And this is totally wild speculation, but it basically says that if you consider strings propagating in 10 dimensions, and you think about 9 spatial dimensions as being a 9 torus, for example, think about T9 cross time. And the universe is filled with the thermal gas of strings. Let's imagine this scenario. Then there are winding modes around the cycles in the torus, and these winding modes arise from strings wrapping these cycles. And a winding mode carries a certain energy. You can wind the opposite way, and you carry the opposite energy. And these things can annihilate when there's a confining potential that puts strings with a certain winding and strings with the anti-winding in the same place. Now, these annihilations can be described in terms of quantum field theory on the string world sheet. And it turns out that the dynamics of these annihilations is such that certain dimensions of this torus remain such that they can emit these winding modes, and certain directions these windings will annihilate. And what ends up happening typically is that there are 3 spatial directions that are left unfrozen after the winding. And this is maybe an explanation for why there are 3 large dimensions plus time. So this mechanism is called the Brandenburger-Waffe mechanism. It was proposed in the mid-1980s. People have looked at this in terms of string gas cosmology, but it's sort of an argument by dimensional analysis. There's really no firm basis to believe this idea, but it's sort of the best idea that's arose so far.
I'm just curious, what properties of field theories in 4 dimensions are special that you are thinking of?
I think I'm thinking about how the coupling in 5-4 theory, for example, is dimensionless. That's sort of unique to 4D. That's the initial thing I had in mind. But I imagine that normalization in general has properties that are dimension dependent. So, for example, in higher dimensions, you could have non-Lagrangian theories, and yeah, I think if you want a Lagrangian theory with certain properties for your quantum field theory, then maybe their dimensions are preferred.
Okay, well, thank you. That covers me. Doing one last glance around the room, it seems like you've covered everything, and we've taken up more than this time than you volunteered. So thank you very much for giving us that extra time. And yeah, thank you very much.
All right. See you next week.
A really nice talk, and we're looking forward to seeing you next week.
All right. Thanks.